Hello everyone, this is the part 2 of Photochemistry Rapid Revision Notes. In this video, we will discuss about the kinetics of photochemical process in unimolecular system, and then we will discuss quenching and Stern-Volmer equation. So let's start the video. As we have discussed in previous class, when any electron present in the singlet ground state, it absorbs light and goes to singlet excited state, that is S1 state. Rate for this step is R equals to IA because here only absorption is occurring. Then next, after electron going in the S1 state, there is possibility it can again come back to the ground state and produce heat, or there is also chance produce light, that is represented as H nu. Then next possibility is it can transfer into S1 to T1 and release heat. After going to T1, there is possibility that from T1 electron can come back into singlet ground state and producing heat, or similarly either it can produce light also. So these are the possibilities. Now we will write the rate equation for all of them. So the rate equation for the second step is R is equals to, here we are representing rate constant as KIC. IC means internal conversion. In the previous video we have discussed when any electron transfer from same state, then it is called internal conversion. Then the third step rate equation is KF S1. Here KF is the rate constant for fluorescence. Then the fourth step rate equation is KISC S1. Here ISC represent inter-system crossing. Then in fifth step rate is equals to KISC dash S1. Same here also. Then the last step, sixth step, here rate constant is represented as Kp. Kp is rate constant for phosphorescence. These are the steps that involve in the molecular transitions. We will apply the steady state approximation. So using steady state approximation, where we are not solving in details. If you want you can solve. I will just write the direct formula. What is steady state approximation? In this case, rate of formation of S1 is equals to rate of decomposition of S1. After solving, we will get the value of S1 is IA by KF plus KIC plus KISC. And for T1, we will get KISC by KISC dash plus KP into S1. Similarly, we can write for the quantum yield for phosphorescence and fluorescence. So the quantum yield for fluorescence is rate of fluorescence by rate of absorption, which can also be written as Kf into S1 by Ia from the above. Like Ia represent the rate of absorption and Kf is the rate constant for fluorescence and S1 is the singlet state. Similarly, we can also write rate quantum yield for phosphorescence is Kp into T1 T1 is triplet state here by IA. IA is rate of absorption. Then next we discuss some relation like rate constant for fluorescence is equals to 1 upon T naught F. T naught F represent intrinsic fluorescence lifetime, and the rate constant for phosphorescence is equals to 1 upon T naught P. T naught P is similarly intrinsic phosphorescence lifetime. For the fluorescence, we can also write Kf plus KISC plus KIC. IC is internal conversion and ISC is intersystem crossing is equals to 1 upon tau F. Here tau F is the actual fluorescence lifetime. Kp plus KISC dash is equals to 1 upon tau P. Here similarly tau P is actual phosphorescence lifetime. We can also relate quantum yield for phosphorescence and fluorescence with the lifetime of the fluorescence and phosphorescence. So we can write relation like psi f is equals to kf by KIC plus KISC plus KF. That is tau f by tau naught f. And next, quantum yield for phosphorescence is equals to, here the term psi tau is equals to Kp by KISC dash plus Kp. This is called quantum efficiency of formation of T state. So this is all about the fluorescence and phosphorescence. Now we will discuss quenching and Stern-Volmer equation. If we not add the quencher, then our quantum yield for fluorescence is Kf by KIC plus Kf plus KISC, and after adding the quencher, then it will become Kf by KIC plus KISC plus Kf plus Kq into Q. Here Q represent quencher. If we will take the ratio psi f naught by psi f, it will become KIC plus KISC plus KF plus KQ into quencher. Divide by KIC plus KISC plus KF. In short, we can also write it as 1 plus KSV into Q. Here, KSV is the Stern-Volmer constant, which can also be written as 1 plus KQ into T naught F into Q. Also, draw the graph, that is psi f by shift as 1, because in this equation we can write it as y is equals to mx plus c. So in y we are taking psi f naught by psi f, and in x we are taking the concentration of quencher. So the constant term is 1 and the slope is KSV, or we can write it as KQ into T naught F. So this is all about the quenching and Stern-Volmer equation. Next, move to excimer or excited state dimer. Let's suppose we have the substance A. When it add with the another A in presence of light, it form after collision it form one excited state molecule and one ground state. Then again both combine and form excimer. There is another possibility also when two A molecule combine and form AA, and in presence of light it form excited state dimer. Then next we can calculate quantum yield of reaction, which is equals to number of molecules reacted by number of quanta of radiation absorbed. So energy absorbed per mole, that is 1 Einstein. We can also write 1 Einstein is equals to number of Avogadro number into h nu. Now there is some important definitions like alpha phosphorescence. It is also called as delayed fluorescence. It is of two types. The first one is E type and second is P type. E type is also called as eosin type and P type is called as biphotonic or pyridine. Beta phosphorescence, that is called normal phosphorescence. In P type, two molecules of triplet state combine and form intermediate. Here intermediate can also form by S0 plus S1, singlet ground state and singlet excited state. When the transition from S1 to S0 plus H nu. When transition occurs from the singlet excited state to singlet ground state and it releasing the light, that is H nu. Here actually two molecules required to create two triplet state. This is all for this video. There are still some important points that we will discuss in the next video. So thank you for watching this video.